Thanks everyone for coming to the QFT Physical Mathematics Seminar. Today we're really happy to have Matthew Yu from Oxford. He's going to tell us about a new tangential structure for type 2.
Great. Yeah, thanks for inviting me to give a talk. It's really nice. It's my first time at CMSA. I want to talk to you about some work that I put out last year with my collaborator, Arun Debray. And in this paper, we propose sort of an answer for a question that's very important in the context of string theory. And we're hoping that sort of the result in this paper can be built off of to sort of answer some long-standing questions that are like by now 25 years old in string theory. So I want to begin with a couple of, because this is a physical mathematics seminar, I want to begin with a couple of physical motivations. And the first physical motivation is that sort of I want to understand, like, in the context of quantum gravity, what you need to know is you need to know sort of the structure of basically of string theory. Mind. And a way to sort of think about this is via, you should think of this kind of via this this sort of quantum gravity cobordism conjecture, which basically says that sort of the full tangential structure for whatever the quantum gravity theory is supposed to be, like this cobordism group has to be 0. So therefore, what I want to answer from this is sort of what is the right bordism group for kind of type 2A supergravity in a sense. And you should think that really gravity is the theory of kind of like gauge tangential structures at the end of the day. And so if I can approximate what the tangential structure for type 2A is, then I'll have a good understanding of sort of the defects and things like that should come from the string theory. So in this paper by Mcnamara and Vafa, basically by kind of approximating the tangential structure, right? They were able to kind of derive the fact that string theory must have, say, D branes or like O6 planes and things like this. So therefore, understanding the tangential structure and getting closer and closer to what the actual answer is supposed to be will give you some understanding of sort of what are the extended defects that have to be in the theory that basically like close up all of these bordism groups. Sort of this is a very hands-on way of understanding some aspects of quantum gravity. So the goal of this talk is basically the goal of this talk is to sort of answer this question. In terms of like the mathematical motivations, there's sort of many different things that you could, there's sort of many computations that you can do in the world of spectra. So let me just tell you some spectra that are commonly used, and these types of spectra, maybe kind of, you could just say kind of QFT in the QFT context. The spectra that you'll kind of run into is empty spin, maybe empty spin C, empty, and kind of at the end of the day, you might have empty string once you go into like heterotic string theory. Sort of these two things come up, and I guess there's also MTSO if you like bosonic things. And this is sort of like a way of thinking about sort of what type of system you might have. So if you have fermions, or if you have kind of charge or fermions that are kind of charged under a U1 bundle, then you might have a spin C structure. So at the end of the day, these are the kind of the common spectra that you want to study. And to study these types of things, you might want to compute some bordism groups out of these things. You might want to actually compute, the homotopy groups of these spectra, which are supposed to be bordism groups. And then, but to do that type of thing, you can make some approximations. So you can make some kind of approximations. low degree, you can have a map, say MT spin KO, MT spin C KU, and then MT string to TMF. And this works in sort of low enough degree. And the reason why this works is because what you want to do is you want to feed this into some sort of atom spectral sequence, and it's much easier to compute over kind of KO or KU than it is with MT spin. And so for a long time, my collaborator Arun and I, we've done lots of computations like this, and sort of we know that sort of these types of simplifications exist for these three spectra. Now there's also this question, which is that sort of there's also TMF 1-3. And then there was a question of kind of what is the right spectrum that looks over here that gives you a map to TMF 1-3. And so kind of computationally we were sort of led to this question because we wanted to say that okay, there's something here that you can actually get your hand on, but like what is the actual like big tangential structure that's actually there? And so today I want to propose sort of the answer to this thing. And the answer to this is going to be string H. Is going to be the tangential structure. So I'm going to show you that there's sort of an orientation of TMF 1-3 by MT string H.
Whatever TMF 1-3.
So in terms of like, yeah, the reason why is because if you want to do sort of computations along these sides, it's good to remember that you have you can read the cohomology of something like this. You get that this is sort of over the Steiner algebra over A1, 2. Similarly for these two things as well. Here you have kind of something over E1 over Z2, the TMF case. And here, there's also something similar. This is just something that kind of people have shown. And by using this change of rings, it's nice to sort of compute over just like, instead of the whole Steiner algebra, this is like very much more easy to compute over. So E2 is in particular another type of module you can look at. And so this is just something that computationally was always there, but we never actually had a purpose to use it, right? Like if you wanted to compute anomalies for like fermionic systems, you would say, okay, great, it's some sort of spin structure and maybe some spin structure plus some extra bundles and things like that, and you compute some Borism group for this. But we didn't know sort of what is the right context, like what is the right physical context to use this type of simplification. We know we can use this type of simplification if we care about heterotic strings and this type of things for like if you have fermions with sort of some U1 background. And the context of this is going to be sort of type A, basically. This is sort of like you ask the question first because you have some sort of computational thing that you can get a crutch on, but you don't know what the physical context is. And so I want to give you some physical context and motivate sort of what this thing is. Does that answer the question? Right. So just to summarize, kind of the orientation, sigma goes to MT, goes from M string. Yeah, now this is sort of Ando. So this orientation is due to sort of this this P1 is basically saying that P1 is over 2 is the string structure, and this sort of due to anomaly cancellation, it's like kind of the Green-Schwarz anomaly cancellation.
We have a question in the chat from Vivek. He says heterotic backgrounds include the data gauge bundle, so perhaps one should generalize to twisted string structures. Will these appear in the present discussion?
Yeah, so that's a good question. Indeed, you can do the analog as well for the twisted string H case. That's sort of, yeah, it's sort of work in progress. And I'm only going to be talking about basically the R sector at the moment, but indeed, if you throw in like the intersector, then you will have twisted structures. But let me, yeah, I think I'll make a remark about that then. So anomaly cancel. And then, and so the question is sort of question. Are there some analogous? Are there some analogous anomalies for other and if there are, like, what is the, and kind of, yes, what is the tangential structure? Is. So this is sort of the other part of the story, is that kind of there's a physics question here that you might want to ask, and indeed I will kind of introduce for you what the anomaly is supposed to be in the context of 2A.
So the one on the top is the heterotic string.
Yeah, this is for the, that's right, cancellation in heterotic. So, okay, so hopefully that was some sort of motivation, and our story can kind of begin here. A while back we asked this mathematical question, and so our friend Sanath, so Sanath Devalapurkar, who's a student at Harvard, showed that whatever that empty string H, whatever the heck it is, has a map to TMF13. So kind of today, so we upgrade this to an orientation and so kind of we take Sanath's thing and we actually realize that you can actually do a little bit more with it. And what I want to do is I want to, so the goals of here is like kind of what I want to accomplish with this is I want to relate string H with a W7. So this is integral W7 with 0 anomaly of Diaconescu-Moore-Witten in a paper that they had in 2000 in the context of M theory slash and then this is sort of like the nice like physical thing that's like that you should actually be expecting, and then some applications. Using string H for anomaly cancellation. So this goes back to kind of the first point about this cobordism group of gravity being 0, that basically that all global symmetries, or that you should have no global symmetries, and therefore kind of all symmetries have to be either broken or gauged. They have to be gauged, and like any anomalies associated to any symmetry must vanish. So you can kind of compute the group that classifies all such anomalies, and you can use the string H structure, which turns out to be much more useful to compute with. And then I might remark on some sort of remarks on kind of twisted twisted string H. And maybe a little bit about, sort of speculations. Again, work in progress about what happens on the 2B side. So I want to start with the slogan. I think this is like quite for someone who thinks about kind of tangential structures a lot. I think the slogan is actually quite helpful. And then I'll make this slogan precise. So what you should think of is string H is the spin C analog of string. So let me first review for you a couple of ways of defining a spin C structure. There's multiple ways of defining a spin C structure. So let me give them to you. I'll define all the ways of doing a spin C structure, and I'll kind of show you that like really string kind of parallels all the different ways of defining a spin C structure. So a spin C on an oriented manifold, an oriented bundle V over X is equivalent to one, a trivialization of the integral box gene applied to W2 of this bundle. So this integral box gene is a map from the two coefficients, H3 Z coefficients. Or you can say it's equivalent to also a class C1 side H of X and an identification of C1 mod 2 with W2. So this is kind of a twisted spin structure, or the data of a complex line bundle. L and the spin structure. Plus L. And what I mean by spin structure on B plus L is I mean that W2 of B plus L is equal to 0, and also W1 of B plus L is equal to 0. Other ways you can think about a spin structure. So now, yeah. Good. So now let me introduce string H, but first let me select B over X, B of spin C, B of spin C. So what I'll basically do is I'll take like spin C. I'll take something that's already spin C. I'm gonna add on like some more conditions to this, and I'm gonna kind of build string H from this, and then we'll see kind of the big picture that's gonna emerge from this. And you can take sort of and the complex. I want to define I want to find something called lambda C of B, which is lambda of B plus L, where lambda is equal to P1 over 2. And it's easy to sort of think about it in this way, sort of lambda C, you can kind of expand it out and it becomes P1 plus the squared all over 2, if you like to. So, and in this case, yeah, so then definition H structure on plus spin C so I want kind of an analog of this integral box chain thing, except now I'm going to say box KU, whatever this is, of lambda C of B. So I want a trivialization, sorry. KU7 of X. And so how should you think of this box KU? It's sort of the connecting map, where if I take sigma squared of KU, by the bottom half I can go to KU, and then I can kind of truncate down to HZ, and there's a connecting map. This guy. Or I can look at order class. The class C1 KU.
Sorry, I didn't get the connecting.
So it's a thing that takes something in integral cohomology, and it basically connects to something in sigma 3 of K. So that's why it so this is a degree 4 thing because it has something to do with P1, and then it lifts it to KU7. Class in C2. This one maybe KU class and an identification. You kind of truncate this guy from K theory. This equals lambda C of B. So this is basically the second condition. Or you can think of it as, and the third condition is, so I'll kind of write it down for you. It's a BUS twisted string structure. US is a string structure for S over BU. And when I say twisted string structure, I mean that when you take tangent bundle of your manifold and kind of you take the tangent bundle plus this one, and you have a string structure on the tangent bundle plus this one. So it's kind of the analog of this one, where I have a spin structure on the bundle plus on B plus this S. So the analog is that it's the analog of this statement, where instead of a string structure, I had a twisted spin structure. So it's nice to use these in kind of different ways depending on sort of what you want to do.
Why do you call it string instead of string C?
So string C is something that actually already exists in the literature. And string C, so the way that it's been introduced in the literature, they have also a class, so for string C. The condition is that lambda C is equal to 0 on the nose. Whereas here I demand a trivialization of like the list P theory. The merits, there are some merits of this. The merit is that manifold with string C structure has kind of has a spin C on its loop space. So on the one hand, this is kind of nice because it's sort of paralleling Witten's story about sort of string, and then you can have a spin structure on loop space. But the cons, I should have pros. But the cons is that this is way too strong. Be a structure for there. And the reason why it's way too strong is because if you turned off the bundle, if you turned off sort of L inside of this guy, then you would just, so you turn off the C1, you would just literally get a string structure, but a string structure because but kind of so kind of lambda C, you can go to lambda by turning off the bundle, goes to 0 by turning off the bundle, but string is too strong. So that's why we don't use it. But it's called something. And I guess when people were actually studying string C, they wanted to tell sort of the analog of like the Witten genus story for in terms of like kind of going back to the slogan, indeed, we know that there's sort of this sequence. A, Z, 4, and then sort of what happens string H is that there's a map here. Let's see. This is KU7. Maybe I'll write this. This, of course, that's this direction. So indeed, it's sort of it's the spin C analog of string. And just as a quick check, so indeed, if you are string H, then you're also spin C. And so you pass the first test of being a structure for type 2A, because type 2A makes sense. Spin C, because it's coming from kind of the U1 bundle from compactifying M theory. So already, this is good. So it passes that test. Now,
So that circle is, I mean, there's a field attached to that circle. What field is that in type 2A? To the central circle in spin C.
Yeah, so good. So basically there's sort of a flux quantization of this guy. It's like equal to W2, maybe mod 2 reduction over here. So it has something to do with like the F2 field. Yeah, well, I'm in the RR sector.
It's one of the Ramon fields here.
Yeah, exactly. That the Ramon field has a flux quantization condition in type 2A.
Yes, but I think of that as being one for all of the Ramon ones having to do with complex K theory. So how does that fit with this?
So this is actually, like, indeed, this is a good point. You'll kind of see how this is, you'll see how this plays out a little bit more. Sort of the data for a string H is actually kind of, it's related to a K theory class, which I haven't said yet, but I'll say in a bit. I'm just kind of showing you that there is a spin C structure in 2A. But indeed, there's something related about like a K theory, really a K theory lift, right? Because what you really want is like a lift of this thing to KU4, right? And so a string H condition is, if you sort of pick the analog of what this thing is for spin C, what it is basically an integral W3 is equal to 0. But this thing, sort of what it has is basically you have a lift of this thing to a class in like KU4. So that's another way of thinking, like that's the way of kind of unpacking the first one for string H. So it is something about like KU4. I guess a thing to pay attention to is that you know, the tangential structure at the end of the day for string theory, whatever it is that you like, because there's no symmetries, the tangential structure must be generated dynamically. And so you look at sort of the quantizations of all of the fields that you have in type 2A. So kind of there's F2 and F4, and anyways, they respect some quantization conditions. So you have to kind of see whatever the right structure is that matches the F2 condition and the F4 condition.
I mean, there is a story with K theory, but also involving self-duality. Involving the Ramon field and certain anomaly cancellations, etc. And so, are you saying you can duplicate that better?
What is the story you have in mind when in terms of the self-duality? Are you saying I can make a?
I don't want to. So
okay, I guess that's maybe a separate question we can discuss later. I just wanted to convince you that there was a spin C structure in type 2A actually. So we're on the right track. But I wasn't planning to say anything about self-duality here. Another way, but anyways, I just wanted to say that another way of understanding this condition is basically a K theory lift of this class lambda C. So it has something to do with K theory. Good. And so I don't know what to erase. This. Just a mark. So kind of what we do, and I won't go through all the details, is that you can form the spectrum MP string H, and kind of what's really nice is that this last condition, right? This last condition says that it's complex oriented. But what we can do is we can kind of take this and we can use the third definition and see that this is MT string smash mu. And from here you kind of apply you kind of through a sequence like maps. And this is hiding a lot of details. There's a lot of kind of E-infinity stuff that you have to like make sure that's all there. But that's taken care of formally by the work of other people, namely Approximating and Hill-Lawson. And so kind of using this, we were able to actually provide an orientation of TMF. And so this is the main theorem. Our paper. So that's all I wanted to say kind of mathematically about this thing. I will of course spell a little bit more about like the homotopy groups of these things, but indeed you already see that kind of with the structure you get something kind of nice. You see some kind of even degree classes coming in here, some things from T string. So I'll say a little bit more about that, and then pack a little bit more of this when I maybe give like one example of how it can be used for anomaly cancellations. But now I want to say a little bit more about what this has to do with the W7 story. So far I haven't said W7 at all. So tying it back like that with W. And so good. And so the punchline, actually, maybe I'll sort of give the background a little bit for why the W7 is even there. It was studied, so this W7 zero condition is needed for defining the topological sector. The partition function. And so very roughly, if you just consider this G4 field inside M theory, the partition function of some scalars is given by a sum alpha over H4 manifold -1 that adds alpha e to the G alpha. So this is G4 as drawn before. And so basically kind of a gauge transformation under specific gauge transformation. Alpha goes to alpha plus 2 gamma. You want to make this understood again. Basically, if W7 doesn't equal 0, then the partition of Z vanishes. The manifold. So what does this mean in the kind of in what sense is this an anomaly? Well, if you study string theory and you sort of take it very seriously, that's supposed to be a theory of quantum gravity, we're supposed to do some sort of gravitational path integral. And so this is a partition function. And so sorry, in the gravitational path integral, you're supposed to sort of sum over all manifolds of all topology. So you kind of look one manifold at a time and you say to yourself, okay, is this manifold consistent? Well, you study the partition function of it and like it vanishes. So if it vanishes, then like it shouldn't be something that you put in to the gravitational path integral at the end of the day. So it's an anomaly in the sense that if you want to include such a background for type 2A into like the grand gravitational partition function, you better have this be equal to 0. So that in that sense, it's a consistency condition for type 2A. Like if you want the manifold to actually contribute to like some of the topologies. But this is
That's strange. It's not an inconsistency in the theory.
it's sort of that's right.
In quantum field theory, there are manifolds, for example, in three-dimensional topological Chern-Simons. There are lens spaces that have 0 partition functions.
Yes, the theory still makes sense. Yeah.
Theory.
Indeed. The theory can still exist even if the partition function vanishes. So it's which is why I had to qualify what I meant by an anomaly. But if you believe that sort of right, like kind of if the manifold that you want to put the string theory on, kind of evaluate it on, is supposed to contribute to like the grand sum which is the sum over all topologies, then if it's 0, then like it doesn't make any contribution. So I want to say that I want to actually sum over all manifolds with some non-trivial contribution to the path integral. That's what I call the anomaly. That is maybe the qualifier. So let me call this a DMW structure. So I'll call this the DMW structure. DMW structure. I'll define it as kind of like a spin C, right? Like I have a spin C structure, and I also demand this W7 goes away. So now there's a question. Right, there's a question, which is given W7, kind of when it is X also string H, and vice versa. So so it turns out the vice versa way is easier, which is a string H structure reduces the DMW structure. So okay, so this is something that you can prove. And to sort of to prove this, I would like to use the first definition of the string H, which involves a trivialization of lambda C when I apply Ku Bochstein. So you can observe the following commuting square. Observe so I can take lambda C inside H4X Z, kind of apply the identity. On this side, I use this thing, so I got something in Ku X. Here I can kind of restrict 7, 0. So this map over here, it's kind of this map over here is going to Bochstein square 2 applied. So let's see. So if you apply Bochstein square 2, so if you apply this to lambda C, then you just sort of do computation. What you want to do is you want to use some sort of mod 2 reduction of lambda C. You get it in terms of W4, and then you use the kind of the Wu formula for this one, and you see that this basically gives you an integral W7. But I'm using the definition that the top line is trivial over here. So then when you strip this one, right, you get that this is trivial. So this thing implies this thing. To go the other way around, now you want to go from and this is really the question of kind of, I know DMW is really there. In what sense can I use string H? Actually, so for spin C, well, then if you have a DMW, then W lifts basically this extra structure doesn't really buy you much in dimension 5 and below, like spin C was already kind of good enough. And what you'll see is that kind of string H is really a very, very important thing in high dimensions, which is good. Like we're trying to answer the question about the background for like 10-dimensional 2A. Dimensions 6 to 9, you see that spin C is not equivalent to W. But in this case, but still kind of averaging W. This H. This is not a hard thing to see until you get to degree 9, in which case it requires a computation. And in degree 10, so in kind of dimension 10, we don't know. So I guess to summarize, right, like kind of DMW said something and we're saying, okay, let's take this, push it to string H. In 10 dimensions, indeed, like maybe like in 10 dimensions, indeed, there's sort of a problem. Like you know that like DMW is kind of given to you in 10, but you don't know if you can actually like pass it to string H. By some other arguments of kind of looking at the F4 flux, you see that string H is like quite close, but it still misses like a little bit. But the spoiler is that even though mathematically we can't prove something about kind of W7 equals 0 implies this, physically speaking, this is actually quite a good structure. And I just want to give a quick application. So quick application. So you want to compute some sort of Borism group. So imagine some sort of anomaly cancellation. Suppose the group that you wanted to compute was some sort of spin C W7 of like VG. Very often G will be a simply active V group. Sometimes it's not, but in this case, it's actually quite nice. I suppose you lift a string H. You can lift this. Lift it to string H. So suppose you have something in kind of low dimension, where like it actually does lift, and you try to choose the lift, and you do the lift. And then all you have to do now is just understand some Borism groups. String H of VG. But this is not so bad. In fact, you can actually kill the problem sometimes with just the Hertz once I give you the homotopy groups of string H. And the homotopy groups of string H are actually really nice. Because it's generated as a polynomial ring. There's no torsion. X2, X4, X6, X8, Y8, and some other stuff. So you can kind of do this, and you can find that if bullet is equal to 10 or below, then you have no global anomalies. In this case. That's pretty quick instead of using the W7 thing. So there's a couple of future directions that I wanted to say a little bit about. Which is that the story thus far is really just only the R sector. You can kind of add in B field. And when you add in the B field, then in principle, kind of when you add in the B field, what you'll get some sort of twisted EMW slash, twisted string H. So these are things that you can classify and you can sort of work out what these twists should be. There's a way of doing this kind of laid out by the paper of Ando, Blumberg, Mcnamara-Hopkins-Rezk. So anyways, this is some kind of theory that we're still working out at the moment, but I think we know the answer for how to do this. So kind of so another thing you can kind of do at this case is you can apply T duality. Apply T duality, where your background X was some N9 times S1, and then in this case, you land in type B. X, kind of, which has a twisted H structure. And so, okay, and then you ask yourself, like, what am I going to do with this? There's sort of a long-standing question in the type in sort of the type 2B string theory literature, which is sort of how does S duality, like, how does when was interactive with sort of the X3 field and the H3 field that you get in here. And what do I mean by this? I mean that sort of inside this world, these things are supposed to really live in kind of this thing is supposed to live in this twisted A theory. So it's really kind of a tension between something about modularity being like playing well with this thing that lives in twisted K theory. Somehow, when you consider one of the differentials inside this twisted K theory thing, it actually isn't invariant on an S duality. So it's kind of weird. It's there's been things in the literature that's hinted at sort of maybe like twisted K theory isn't sort of the right thing to be considering quantization of these types of things. Maybe it's something else. And my hope, the hope is that sort of by using the orientation that we saw for string H, because it orients something in kind of in TMF, which is kind of an elliptical homology, maybe the right thing to do is to consider kind of the pair of F and H as something that actually lives in not just like twisted K theory, but something in TMF. And then together we may be able to actually like resolve this S duality problem. So there's lots of details here that I'm glossing over, but kind of one merit of this orientation may be that you can actually answer some question. This is sort of ongoing exploration. So I think I'll stop there.
So, do you have any questions? Any questions over Zoom? I will welcome you to the back. From a purely mathematical viewpoint, without invoking DMW's partition function-based reasoning, can you motivate in words why one should mathematically expect W7 to be related to a string H structure in the first place?
That is, yeah, I don't see why purely mathematically you would go for such a thing. I think kind of, yeah. What we had is we had an understanding of string H because our friend Sanath told us something about it. And then we were saying, hey, it's related to a W7 thing. And then we went out and we looked for a W7 thing. I mean, if you knew what string H was for some reason, then you'd see that it's related to W7. If you just started with W7, you probably wouldn't necessarily go to a string H. So that's my take. Like string H implies it implies this W7 equal to 0, but I wouldn't necessarily think of taking W7 equals 0 and trying to lift to something that's a little bit stronger than this abstractly.
What if W7 is non-zero?
Well, W7 is non-zero, I guess. So, I mean, you definitely don't get string H from that. W7 not being 0 is, I guess, a physics question of relating to kind of how seriously do you take this DMW thing as sort of being like an actual condition for a consistent background for type 2A. But you definitely don't get a string H structure.
There's no more questions. Let's thank Martin.